There we go. Hopefully I'm both audible and visible here. It should be at this point. Well, why don't I go ahead and get rolling here? I think we're got a few folks here, and the first part is a minute or two of repetition here to remind us kind of where we were and let you know where we're going today. Today is going to be kind of a nuts and bolts session. The idea here will be to go through a particular example here in a fair amount of detail, perhaps more detail than I will in future ones, because I'll be sort of describing to you the way we're going to sort of set up the modeling, the models themselves, as well as the R scripts to drive the modeling, and the rest of the examples that we'll be doing will use essentially the same framework. So spend a bit more time today on that. So why don't I jump into it? So the example I'm going to be talking about today is actually going to make use of what we started to touch on last week. Let me go ahead and bring this up. Okay. So we talked a bit about modeling data when we've got it in the form of sample means of some sort of continuous outcome. And that's what we're going to be working with today. So we're going to be working with ones where we're going to describe our sample means here as being as samples from a normal distribution with some mean, where that mean is possibly a function of a number of things, including things like drug treatment and maybe things like mean patient characteristics and such. And then we've got our measure of uncertainty in that mean, then our standard error in here. And initially we'll do an example where, like this one, we're going to be estimating that parameter sigma squared, which characterizes that uncertainty. We'll also do a variation on that, more like the one here, where we use the observed standard error instead of using a model estimated one. Later on, I guess this will be next week, we'll talk about using a model where we actually still use the observed standard errors, but instead of treating them as covariates, they actually become dependent variables in the example that we'll do next week. So let's jump right into it here. Let's go jump back down to our example. Okay, here we go. So the example we're going to do is we're actually going to attempt to sort of recreate the example that Yatmandama and others did for the gemcitabine statin combinations. So recall that was actually the first paper I described during our first session to illustrate model-based meta-analysis. So we're going to be looking at the dose response of gemcitabine statin combinations compared to both statin monotherapy as well as to statin ezetimibe combinations as part of this. And this is sort of recapitulating what was done as part of the gemcitabine development program. So we're going to pretty much follow along with the example that Mondema did, largely replicating it. Differences from the original analysis, as I say here, are, in our case, we're going to use a Bayesian method, although we're using largely uninformative priors here. So frankly, you can think of it as being just sort of a fancy maximum likelihood example in this case. The other part of it is I did not have access to the gemcitabine data because that did not come from public sources. So we're going to fabricate that. So we're going to simulate that data for this example. So please don't cite the data that's in here because not all of it's real. But the remaining data that are in here were extracted from public sources. So our objective here, the objective of this analysis, if we were doing this in the real world, if you like, it will be to assess the benefit of gemcitabine add-on therapy, add-on in this case to statins, relative to marketed treatments, particularly ezetimibe-statin combinations. So the data we're going to work with here are sample means for percent change from baseline in LDL cholesterol. And this will be at study endpoint, so we're not going to deal with longitudinal data in this example, just study endpoint. The data came from 25 studies that contained 154 treatment arms overall. And the data then reflects, well, these are going to be sample means, but they reflect individual results from over 9,000 patients. Treatment duration varied in the studies as we look across them, going from 4 to 16 weeks. Some covariates that we have available to us. We've got baseline LDL as well as treatment duration. Let's see, in the example I'm going to show you, I know I'm not using treatment duration. I'm trying to remember if baseline LDL is in it. I don't believe so, as we did. We'll see in a moment. So our sort of immediate objective here is going to be to construct a model for LDL percent change from baseline as a function of drug and daily dose and possibly other covariates. And so this is pointing to the data file, and actually this is a good time to point to this information that you actually have in the course distribution. Let me show that to you here. What you're looking at here is the contents of, well, they're my directory here, which has a few extra things, but it's essentially a superset of what you have from the course distribution. And in particular, you should have a directory called statin gemcitabine. And so the example we're going to do is going to be using data from that. The data set itself is right here. It's called ldldata.csv, so it's just a comma delimited file. Let's go ahead and take a quick peek at that. Let's make that a bit bigger. Hopefully that's reasonably visible to you. So this is the data set we're going to work with. You can see you got our headers here. So the first column is just some descriptor of the trial. So we've got a number of trials with different designations here. Drug 1 in this case would be the statin that was administered for this particular treatment arm. And I guess I should mention each row here corresponds to a treatment arm within a study. So we've got our trial, we've got our identifier for which statin, if any, was used, and then an identifier for which non-statin. So drug 2 here corresponds to the non-statin. So that's either going to be none, gemcitabine, or ezetimibe in this case. We've got the dose 1 would be the statin dose in milligrams per day, and dose 2 would be the non-statin dose in milligrams per day. The sample size that was used to calculate the summary statistics. Week here corresponds to the study duration. And then this LDL PCFB stands for LDL percent change from baseline. So you can see the values we have here. LDL 0 is the baseline LDL measurement in that same treatment arm. And then we also have a couple of standard errors, one for that baseline and one for the LDL percent change from baseline. If you notice as you scroll down through here, as I recall, we don't have standard errors for all of the studies. There are examples where you'll see NA where we don't actually have that information. Well, there's a reference indicator here, but I don't actually have the reference list anymore, so those numbers aren't too useful to us. So we'll ignore that. So that's the data we're going to be working with. Let's actually take a peek at what that data looks like. We go. Okay. Here we've got some plots of the data. Again, we're looking at sample means here. You can see there's a different set of panels for each one of the statins, and this page is just for the statin monotherapy results. And here, each panel in each group is a single trial, and they're plotted as LDL percent change from baseline on the y-axis versus the statin dose in milligrams per day on the x-axis. So here you can get a picture of the atorvastatin dose response as observed in what do we got here? A dozen studies here. You can sort of see a pattern that we'll consistently see through the various statins. We see something which looks pretty much like an Emax model going downwards here. And you can go across the various statins and see more or less the same sort of pattern, but apparently somewhat different potencies. Next page here, we have our two non-statin therapies that we're looking at. And here we've got our monotherapy doses. So on the left-hand side, we can see we've got 9 trials that involved administration of ezetimibe as monotherapy. And we can get a picture of that. As is known, it does reduce LDL, though nowhere near to the extent that the statins do, but as monotherapy. And then gemcitabine over on the right-hand side, where if we look at monotherapy, again, we can see it's certainly having a clear indication of a dose response and an effect size that at monotherapy actually seems to exceed what you see with ezetimibe, though still less than you see with the statins. And then we've got a number of treatment arms that involve combinations of the statin and non-statin drugs. Left-hand panel here, we're looking at combinations of ezetimibe with statins, and the way they orient you to these things, in each one of these, the blue dose response curve is describing dose response for a particular statin, and you can see they're identified in the heading on each one of the panels. So you're looking at the blue curves correspond to statin monotherapy, and then the red corresponds to the same doses of statin, but with 10 milligrams of ezetimibe added to them. So you can see a fairly constant shift downwards, pretty much independent of the statin dose, it appears, when we look at that. On the right-hand side, we've got atorvastatin combined with, well, different doses of atorvastatin combined with different doses of gemcitabine. In here, we can see, for example, our blue curve here is just our atorvastatin monotherapy shown there, and then we've got various different combinations down here with the atorvastatin. So again, just remind you, down here, we're actually looking at atorvastatin dose on the x-axis. The different curves correspond to different doses of a gemcitabine being added to it. So the green curve corresponds to 300 milligrams per day of gemcitabine added to the atorvastatin doses. The red, the 600 milligrams, and then I'm sorry, wrong way. The yellow is the 600 milligrams, and the red is 900 milligrams per day in here. It's a little noisier because the sample sizes, as you can see, are a bit smaller than we've been looking at some of these other things. So the variability or the uncertainty in these means is a bit bigger. That's the kind of picture we've got just looking at the data raw. What we'll be doing, let's see, do I have more plots or is that it? That was it on the plots. So strategy now is to take this information, construct a model that describes the dose response for the various drugs, as well as how, as well as any potential interactions that are going on between the statins and non-statins in here, in order to try and make some inferences about the potential value of gemcitabine as add-on therapy to these statins, and our comparator here is ezetimibe. Okay, now today, as I mentioned, today is going to be kind of a nuts and bolts day where we'll go through the process of working with a model to describe this. Now, what I'm not going to do is I'm not going to go through the entire model development process itself. Presumably, when Mondam et al. Had put this together, they probably spent some time attempting various models and doing some model selection to try and optimize the model for this when they did it. I'm not going to go through that process. Instead, I'm going to take essentially the model that they had implemented, the model that they had arrived at, and show you how we can implement that using the tools we're going to be using throughout the rest of the course. So that'll be sort of the nuts and bolts we'll be doing. But again, you could imagine some other nuts and bolts we could be doing is actually going through a model development and selection process as part of this. Perhaps we can touch base maybe a bit later on about about the kind of model selection processes and how we might apply that in the model-based meta-analysis case, and how it is, and to the extent which it is the same or different from what you may be used to doing when working with individual data. I guess the short story here is it really isn't fundamentally different than you're doing there. There are certainly, if you're not used to working in the Bayesian framework, there are some differences there from what is commonly done in, say, population modeling using the maximum likelihood methods. But not all of it is different. Okay, so let's jump into the model. Okay, so the model we're going to use, as I say, is essentially that which, in fact, are there any real differences? I don't think there's any real substantive differences between the model that we're going to implement and the one that was done in the original paper, other than the fact that we're going to have to specify priors because of it being using a Bayesian tool for doing it. So what we're going to do is build a model here where we've got essentially Emax models for each of the monotherapy components. I guess we should call it what a inhibitory Emax model really is what it amounts to here for each of the monotherapy components, and then there's going to be an interaction component as part of this. So here we've got the model, and this is kind of written in a form that's fairly consistent with the way we're actually going to be doing it within WinBUGS using the bugs model specification language. So we're going to have a residual variability component here, which is just going to be just a simple normal distribution where we've got our, but keep in mind here, E here for this problem is going to be a sample mean LDL % change from baseline. I and J here I've used to indicate I is indicating the treatment and J the trial. So we're going to have potentially well, in fact, I know we are going to have some inter-trial variation as part of this, though I kept that component fairly simple. Oh, now that I think of it, that is different from the original implementation, because I wanted to illustrate that. The original implementation did not include inter-trial variation, as I recall. Okay, so we've got normal, where we've got some mean. So this is our expected value for our LDL percent change from baseline. Some variation, which is sort of a model estimated standard error then for our predicted value here. And so we're going to be estimating sigma squared as a parameter, and then n is just the sample size corresponding to the particular sample mean. Our model predicted value here, you can see, is written as we've got E0, and to make sure this, I'm always tempted to call this a baseline. It really isn't a baseline in this case. That would really be, if you like, the placebo response. So E0 is what you would predict for the placebo. And then we have some effect due to the statin, some effect due to the non-statin, and because we expect the way this has been set up, the assumption here is that these two E's are probably going to be positive values, and they're subtracted from what you would see following placebo, because we're expecting these things to reduce our LDL. And in particular, we're anticipating that, at least for active treatment, that LDL percent change from baseline is typically going to be negative. And then we have an interaction component at the end, where we're going to take our E-statin and basically our statin effect and our non-statin effect. They're being multiplied, and then there's then you get this 0.01 scalar and a parameter to be estimated, this gamma ij. The underlying rationale back in the original model, as I recall, is they basically started out with the notion that if you had no interaction, but you had a multiplicative sort of effect, what you would expect is that your basic model would look something like you'd have like a 1 minus E statin. Well, you'd have a sort of a baseline value times 1 minus E statin times 1 minus E non-statin is what you would expect. And if you multiplied that through, I'm sorry, I'm messing that up here to be one, because we're in percents. It gets a little messy here. If you did it in fractional decrease instead of percent decrease, you would expect like 1 minus E statin times 1 minus E non-statin. And if you multiply that through, you actually get something that looks sort of like this, but where this gamma would just be 1 in here. So this gamma is being allowed to vary to allow for the possibilities that instead of being a simple multiplicative interaction here, there may be some sort of interaction, which results in this value being something other than 1. The 0.01 is an artifact of the fact that this has been translated to percent. So it ends up that you have to divide that interaction term by 100 in effect to make it all come out correctly to a percent. And then for each of the statin components, we're going to have a sigmoid Emax model. So now you can see here for the statin, we're going to have, you've got our Emax statin times dose raised to some exponent here, indicated as n sub statin. And then you've got ED50 corresponding to that, and a dose, again, raised to n sub statin. What we're going to have here, we have different statin drugs in here, and one of the assumptions that was made is that all statins share the same maximal effect. And actually, the data largely bear that out as a reasonable assumption, but it is an assumption nonetheless. But they vary with respect to potency, and as a result, ED50 will be different for each statin in this model. Similarly, for each non-statin, again, we're going to end up with a sigmoid Emax model. The difference in this case is these are two drugs that work by very different mechanisms. As a result, there's no reason to expect any shared parameters as part of this. So all of the parameters are different across ezetimibe and gemcitabine. Let's see, looks like we got at least one question or comment. Let's see. Can I explain a little more on gamma? I'm not sure if I can explain a lot more on gamma, other than to say that if gamma were 1, you would have that would be a case where you had a simple sort of multiplicative effect of the two drugs, where you would have, again, basically something where it's just like E0 multiplied by 1 minus E statin, and that multiplied by 1 minus E non-statin. That would correspond to that case. If it's different from 1, then that means there's some deviation from that basic relationship. I think I'm going to punt on the question a little bit, because probably the best way of illustrating what its influences are is to basically go ahead and do some plots that show you how the how the dose response changes, and how they interact is probably the best way to take a look at it. One thing that'll, in fact, maybe we can wait until we take a look at the results here, because that turns out to be a fairly important term in terms of showing how gemcitabine and ezetimibe interact somewhat differently. So, as I say, I'll sort of punt until we get there, at least. And if you're really curious, as I say, I would recommend you just plug in some numbers and go ahead and see what happens for the different cases. Anyway, and finally, to keep it simple here, I'm just going to put one additional random effect in here, and that's going to be an intertrial variation in our placebo effect. Essentially, it's like an additive actually, it's sort of like an additive random effect applied to the entire effect. Since saying E0 is normal with some mean, and variance here is equivalent to having something like the overall term plus an eta, where the eta is normal centered about 0. This is just sort of, at this point now we're getting into bookkeeping, where it's just pointing out that the ED50s are different for all of the statins, and we have 5 different statins represented in our data set. It's also, and then for our non-statins, everything is different. Emax is different, ED50 is different, the exponents here, our n's are different. In addition, that interaction component is different for the two non-statins. I guess the other thing I didn't comment on, in the statins, not only are we assuming that the Emaxs are the same, but we're also assuming that that exponent is the same for all of them. Okay, so that's the basic model structure, and the additional thing we have to do, since we're working in a Bayesian framework, is specify some priors. The one thing, if you look across these, for the most part, we're looking at largely uninformative, or if you prefer, very weakly informative priors, with one substantial exception, and this was borrowed from the original paper for I guess during their model development, they ended up concluding that the exponent for ezetimibe, that couldn't be shown to be anything different from 1, so they ended up just assuming it's 1. So for us, that's essentially equivalent to using a prior distribution that's just a point value in here. But the rest of these are all, pretty weakly informative priors for the rest of the components here. I don't know if I want to tell too much of a story on them. You can say I tended to use for a number of these things, use just fairly flat ones, essentially use normals with very large variances, so that they ended up being quite flat over any region of interest that we have. So you see that for like our E0 term, and log of ED50 statin. Notice I'm using log here because I want to constrain ED50 to be non-negative. So that's the reason for using a log normal in that instance. A number of the other ones I ended up using uniforms. For some of these, it makes particular sense. Notice the two Emaxes. Well, we're dealing with a case where you don't expect any of these things to decrease. You don't expect a percent decrease in anything to be more than 100% because that would mean you're getting negative LDLs. As a result, where am I going here? As a result here, I've restricted these things to be within the range of 0 and 100 and just made it uniform over that range. For the exponents, I've used a range that's somewhat narrowed, largely to avoid numerical problems. Basically, when you have an exponent here, if it gets very small, you start running into usually some numerical problems. And if they get very big, that once you get up around 10, you're basically dealing with a stair step, where it's almost an instantaneous increase. So there isn't much point in looking past that anyway. So that just avoids things sort of running off to infinite values or something and ending up with overflows. Let's see, is there any other stories I want to tell? Let's see. Not really. In this case, I used gammas for the precisions, and you'll see this a few cases where we will talk in terms of precision rather than variance. But just remind you, the term precision here is used for the reciprocal of variance. So that's why I'm saying 1 over omega squared for E0 is going to be gamma, or equivalently, that's saying that the omega squared is an inverse gamma with the same parameters. Same thing for our residual variance term here, the sigma squared. Let's see. Okay, that's the point where I think we go ahead and jump in and start getting our hands dirty. I guess before I do that, any questions at this point just on the model as it's been described so far? Okay, I'll keep my eyes open here, but nothing's jumping out yet here. Let me, let's go ahead and go away from the slides here. And actually, let's close the spreadsheet. And let's start digging in into the implementation of this model. I'm going to be lazy, I think, and just bring up the model as I've already done it. I found that sometimes if I do this in real time, things don't work out that well. It's kind of like trying to do a derivation on the board. So let's go ahead and open it up directly. If you want, you can. I'm opening this up in sort of my favorite editor here, but feel free to open it up in anything, including, since this is actually a bugs language model, you can go ahead and open up WinBUGS and look at it in there. Let's see, let me make this a little bit prettier here. Okay, and a little bigger. There we go. Okay, so there's a lot in here, but let me see if I can get you oriented here. So let's actually step back to the main structure here that we're doing. So Let's actually not go to what I have at the top. Let's start pretty much what we've got in here. Now, keep in mind here, notice this is written, it says for I in 1 to n arms. And in this case, the number of arms and the number of data points are equivalent because we're only going to have one sample mean per arm in here. So I'm specifying that. And keep in mind, anything like that where I say 1 to n arms, that means somewhere when I pass the data in, the data has to include that value of how many arms there are. So that's going to get passed in. So it's in this block right here is where I'm going to be specifying the model for each individual value. So, and let's start right here. This statement right here, where I say PCLDLI. Now, PCLDL is the name I've given to the observed data for our percent change from baseline in LDL. So that's what our PCLDL represents. You've got the subscript I, so that's going to be the ith such value. And that's going to have a likelihood then, which is going to be normal. So that's describing our residual variability now. So we've got normally distributed residual variability about some model predicted value that I've called PCLDL mean, again indexed by I. And then we've got some precision. And this is a reminder that in bugs, the normal distribution is parameterized in terms of a mean and a precision rather than a mean and a variance or a mean and a standard deviation. So this is going to be the precision. And this precision, let's see, do I want to jump to that? Yeah, we can do that. Now keep in mind the precision here is going to vary as a function of sample size. So just as I've described it here, so that precision, what I called PCLDL precision I, is equivalent to the reciprocal of the term over here on the right here where you see sigma squared over n sub ij. Well, just so this PCLDL precision I, press I here is going to be n sub ij over sigma squared in here. So, or if you like, if you think of, keep in mind the original precision we talked about was actually 1 over sigma squared. So to get the precision associated, this whole value, I just multiply that 1 over sigma squared by n sub I. And so this value that you see on the right is calculated in this statement down here. This also might be a good point to remind you about one characteristic of the bugs model language is it's not a what do they call it? I always lose track of the terminology for some of the languages here and forget between declarative and the other. But anyway, it's not a procedural language in the sense of something like Fortran or even NMTran or something like that. So the order in which you write the statements is not necessarily the order in which they are executed by the computer. For the most part, statements and bugs can be in any order as long as they're appropriately grouped in blocks. So I can't, for instance, take the statement I've highlighted here and put it outside this for I to in 1 to n arms. I can't put it outside that block. But as long as it's inside the block, it can be in pretty much any order. Okay, so you can see this value up here, the PCLDL PRECI, that has to be calculated here before it can actually be used up there. But again, you can see they actually occur in the opposite order. But they don't have to. I could have actually written this up top. Anyway, so that's where it comes from. So we've got our more fundamental parameter, this PCLDL PREC, which is equivalent to 1 over sigma squared, is there, and I multiply that by n to adjust for the sample size. then our statement after that, we've got to calculate this PCLDL mean. Now that's right here. And this statement here, this PCLDL mean, is actually equivalent to the statement right here, where I'm calculating this E sub ij bar term in here. So that's equivalent to that statement. Similarly, the next two statements are going to be equivalent to the E statin and E non-statin statements here. So you can see that we've got to calculate our E statin, so our statin effect, and then the next one after that is to calculate the non-statin effect. Now, a few things to bring out in here. So most of this corresponds to what we were looking at, but there's a couple of tricks that have had to have been used here. One is we're going to have some inter-trial random effects. In particular, we're going to have an inter-trial random effect on our E0. So we're going to have a trial-specific value for E0, and that has to be accounted for, and that's what's going on right here, where you can see I've got a set of nested subscripts. So I've got this trial component here, which has to be provided inside the data set. So the data set has to provide a set of integers starting at 1 indicating which trial the data is from, and that's going to get used in here. And this E0 itself, the trial specific values of E0 are generated in a separate for loop up here that steps through the trials and generates the trial specific values in here. In particular, the one line to be aware of is right here, where I've got my E0 sub I is going to be normally distributed about some mean, and again with some precision, which in that precision is just our 1 over omega squared for that particular component. Another thing that we have to deal with is that now where'd we go here? There's some things that are specific to particular drugs. So for example, gamma. We have a different gamma for each non-statin. So what's happening here is inside the data set, the approach that I've used here is to have one of the statins indicated by 1 and the other one indicated by 2. And actually, I'm going to have to look at the data set to see which one was which, because I don't remember off the top of my head. I think it was probably ezetimibe is 1 and gemcitabine is 2, but I'll need to double check that as we go through this. So here you can see it's going to grab one of those, and that non-statin value will either be 1 or 2 depending upon what's in the data set. And that trick is used throughout. So for example, when we come down to calculating the statin effect here, where we're going to have statin specific ED50s, you can see that come up here where I'm going to indicate the statins. So the statins are going to be numbered from 1 to 5. And so there'll be a different ED50. So somewhere in here we're going to be generating 5 different ED50s for the different statins, and this will pick out the appropriate one, and that 1 to 5 value has to be provided in the data set. And that again, so other than that, you can see here we've just got a sigmoid Emax model. This is also a good point to remind you that there is no exponentiating operator in BUGS, but there is the POW function, which calculates an exponent. So this statement right here is just saying you take the dose statin sub I, and raise it to the n statin power. And you'll see that being done repeatedly through here. Similarly, for the E non-statin, we've got the same sort of picture, except again, all of the parameters, you'll notice the Emax, the ED50, and the N non-statin all are subscripted by that 1 or 2, well, by the non-statin indicator in here. So again, this block of statements here that I've labeled as the likelihood is nothing more than the equivalent of what you're looking at going from, I guess, from where it says E sub ij down to E non-statin here. And then the last statement where it generates the trial-specific random effect, that's what I showed you again up here in the previous block. And you'll see this sort of approach done over and over again to use different blocks to represent. One block will represent the observations, and other blocks will represent other levels of the hierarchy. Okay, so that's the core model. We mentioned the priors. Let's jump down to those. So here we've got the priors specified. So this is basically doing the statements that you see over on the right-hand side. Most of them are pretty straight ahead. So like here where you see the E0 bar here being normal 0, 10 to the 6th. That shows up as E0 mean being normal 0, 10 to the minus 6. Again, that's just a reminder that we're working with precisions instead of variances. So where you see like here 10 to the 6, that translates to 10 to the minus 6 in bugs here. You can see the uniform is just indicated as D-unif. So like here, that's which one? Yeah, that's the Emax statin, uniform 0 to 100. Again, that's shown up in bugs as uniform 0 to 100 right there. We've got for our log normals. There's different ways you can write this out. I picked my favorite way. So again, here we've written this model for, now we've got a collection of statins. There's actually n statins here is actually 5 in this case. So this is going to loop over 5 values, and it's going to generate the same structure prior for each one. So you can see we've got log ED50 statin is going to be normal 0, 10 to the minus 6. And then here I just convert it back to the ED50. And you may have already seen this in maybe in other courses I've done, but there's different ways I could have written this as ED50 statin equals, the exponential of log of ED50 statin. In this case, I chose to use the left-hand link function instead. They get you to the same place, and either one is fine. Let's see, any other stories to tell? Most of these I think are straight ahead. Here's where I just assigned just a fixed value instead of a distribution to the, which one was that? The ezetimibe. So, okay, so one corresponds to ezetimibe, 2 to gemcitabine here. Yeah, most of that's pretty uninteresting. So that's the implementation of the model. Now for doing some diagnostic plots, we're going to also want to be able to simulate from this model to get simulated values of our observations. So we can compare the simulated to the observed values. The way to do that is there's a couple of things here. Now, we do have a random effect here. So we have a situation where we can get the analogs of sort of pred and IPRED that you may be used to from non-mem. So we can get what I've termed individual predictions right here, which amount to getting predicted values corresponding to what you would predict for a new observation in the same trial in this case. And that would be like, what if you could, do the same trial over again in the same patients under exactly the same conditions, and so it's kind of hypothetical, but imagine you could do that. What do you expect what is your predictions for that, and what's the probable range of outcomes for that. Well, that's what you're trying to answer here. So, and I labeled that as PCLDL con being short for conditional. So it's conditional on essentially the same patients, the same trial in here. So you get, and that would be analogous to IPRED. So, and I often label these as individual predictions. And this is nothing more than an exact replicate. Oops. Okay, this looks identical to the original likelihood expression up here, except for the left-hand side. I've picked a different name. And the difference here is this value, PCLDL up here, corresponds to an actual piece of observed data that's being provided in the data set, whereas PCLDL cond is just a prediction. Okay, but it's a prediction using the same random effect value as the observed data. Whereas down here, we're going to have another set of predictions where it's going to be predicting what's the probable range of a new observation in a completely new trial that just happens to have the same design as the old trial. So what's the probable range of outcomes for that? So we're going to make that prediction. And so I've just given it a different name again here. And the first statement looks more or less the same. The critical difference really comes up right here, where I'm using a prediction for the random effect, which does not tie directly back to a particular trial, to the observed values for a particular trial. And that value is generated up here in that previous loop. So this is basically like just taking our model predicted values for our E0 mean and our E0 precision and simulating from those without updating it based upon having observed data from that particular trial. So that would be more analogous to the PRED value you get, or a population prediction. And that's the term I'll commonly use for those two. So I'll usually call this PCLDL con here an individual prediction, and this PCLDL PRED a population prediction. I think that's all the pieces in the model. Before I jump into the script that's going to drive this, let me take a breath and see if there's any questions or comments. Okay, nothing jumping up yet. Let's go ahead and take a peek at the R script that we'll use to put together the data in order to make use of this model, and that'll be the idea behind the R script. Is it's used to do the data management, to structure the data so it's appropriate for bugs, launch the bugs, and then get the results back and analyze the results that you get back from WinBUGS. So that's here, the statin gemcabine.r. Okay, let's make that a bit bigger. Okay. Okay, so I'm not going to go through every last little bit in this script since it's kind of accumulated a number of things over over time here, and some of them are just sort of details in R than anything else. But there's some important bits that are helpful for you to know if you want to use it as a template for working with other models. And again, you'll see essentially the same script, or at least a lot of components of the script we'll be reusing over and over again. So the first place I start is I just start out with a model name, and my convention is I use a consistent root name for the model, for the directory in which the model is contained, and for the root names of the files. So you can see, for example, this stant gemcabine, that's inside a directory called stant gemcabine. The R script is called stantgemcabine.r. The model is called stantgemcabine.txt. So it just simplifies some of the file management if I just stay consistent in doing that. So there's nothing magic beyond that. It's just convenience. Some of the next stuff is nonsense in order for this to make this script work both in Windows and on the Macintosh here, or on the Mac. So you just realize they don't call them Macintoshes anymore, do they? Anyway, I'm working on a Mac, so that's where some of this nonsense comes in. Actually, I added an extra line here that isn't in the version you're probably looking at. I'll get rid of that momentarily. So most of it you don't need to touch, as long as you're working with the same locations you're currently working in. This is set up in particular. It will work directly with the course materials as you have it on a USB drive. And so you can see here, one of the first things it does is says the course directory. Well, this needs to point to wherever that MI260 folder is that contains all the course materials. This is set up so it'll point correctly in the structure as I recommended it for your USB drive. But if you put it elsewhere, you'd have to change this so it points correctly to the same place. This example dir is where this particular model is located, and this should point, in this case, to that Stanton Gemcabine folder right here inside that MI260 folder. The tools dir, it assumes that the bugs tool folder again is directly inside the course directory, so it has to point to that. The bugs directory points to wherever WinBUGS is installed in here. Actually, this is more complicated than that, didn't I? Actually have a more complicated thing. In the end, Bugsdir has to point to wherever it's installed. The way this is going to work on your machine, it'll end up selecting this choice if you've got it installed on the USB drive. And then you can ignore the wine bin stuff. My Mac will use it, but with Windows, that'll be ignored. Okay, so it does things. First thing it does is it just sets the working directory to where the model is located. It pulls in a bunch of some libraries we're going to make use of, as well as some script files that we're making use of inside here. And you can see a couple of these are inside that tools directory. And this one, I guess I probably should have put it in the tools directory, but I didn't for some reason. It's in the main directory. I set a seed. You actually don't need to set a seed. This will work perfectly well if you just use whatever the default seed goes to. But if you rerun the script again, you'll get completely different results. So if you need to be able to replicate your results, it's a good idea to set the seed yourself. So that's just setting up some bookkeeping. Then we've got, we go ahead and get the data set. So this is just reading in that data set I showed you. It pulls it in. It ends up being in the form of a data frame. When it does that, now we have to grab that and do a little bookkeeping to make it work with our bugs model, recall I'm expecting a set of integers to indicate which statin the data corresponds to. And this is unfortunately, this is one unfortunate quality of bugs. Bugs does not understand text. So everything has to be provided numerically. So we're going to do that in this case by describing our statins in terms of integers going from 1 to 5. And you can see here, atorvastatin, I'm giving the code of 1, rosuvastatin 2, and so on. Similarly, non-statins I've designated either as 1 or 2. And this is just going through the process of making those assignments. So I'm just creating a new entity here that it's called istatin and I non-statin. Similarly, the trials, I'm going to set up a numerical sequence, again, just a set of integers starting at 1, indicating each one of the trials. And from that, I can go ahead and create a bugs data set. So here there's various things that we said we needed. So for example, if we go back here, certain things I have to provide. I have to provide the number of trials and the number of arms. So that's the first thing I'm doing right here in the first 2 lines. So I'm getting those. Also indicating how many statins, recall, and how many non-statins, because that shows up in a couple of places in the model. I have an integer indicating which trial, so I need that, and which statin, which non-statin. So that's kind of all the bookkeeping components. And then we have the data itself, the statin dose, the non-statin dose, the sample size, and the percent change from baseline and LDL. So that's what's going to get passed to WinBUGS. I need to specify initial estimates for all of the I should correct that statement. You don't actually have to provide initial estimates, but if you don't, you usually find the model behaves pretty poorly. So here I'm providing initial estimates. Usually the best way I find for deciding what I need to provide initial estimates for is I go back to my model, go down to where I've specified all my priors, and anything here where I see a distribution on the right-hand side, it corresponds to a value for which I should provide an initial estimate. And that's pretty much how that works out here. So I'm providing a set of initial estimates here. I'm not going to go through sort of where they came from in this case. In fact, I don't even remember where they came from. Some of these you can sort of eyeball fairly well just by looking at the data. One thing I should comment on, especially if some of you learned bugs from someplace other than the courses I've done in the past, is the way we're going to be using R to WinBUGS to actually run bugs, to launch bugs from R. With R to WinBUGS, you can specify the initial estimates in a couple of different ways. You can either, where you're doing more than one chain. So if you want to have different initial estimates for each chain, which makes sense to do, you can do it in a couple of ways. One is you can provide a list of lists where each of the individual lists is a set of fixed values for your initial estimates, and do it that way. Or you can provide the initial estimates as a function which gets called every time a new, it gets called separately for each one of the chains. And then what you would do is you would have that function somehow generate different values each time you call it. And the easiest way to do that is generate them randomly from some distributions, and that's the strategy that you see here. So you can see bugs in it is being declared as a function, and that function is producing this list of values where each one of these, you can see, is generating some value from a probability distribution. And many of these you could probably get rough estimates just by looking at the data. So for example, if we go back to our, let's scroll up here. So for example, if I start looking at stat monotherapy, I can look at it and see, okay, well, my placebo case corresponds to the intercept on these things, and most of them are pretty close to zero. So it seems like E0, hey, zero looks like a pretty good initial estimate. And in fact, that's what I use, a zero. And then I put some variation about that. In this case, I guess I picked a 2, which is actually, I could have argued maybe even using something a little bigger. But that will generate different values every time it gets called based on sampling from a normal distribution centered at 0 and a standard deviation of 2. Emaxes, you can sort of get some idea by looking at how far these go down. And, you sort of look at these and say, Emax, if I look across most of these, it looks like it's probably going to be, somewhere bigger than 60, maybe 70, something like that. What did I actually use? I used 70. Okay. So that you can sort of eyeball. ED50 is probably a little tougher to eyeball. And of course, it's different for each drug. Oops. Each drug, so you'd have to do some more guesstimation around that. But you could probably get a rough idea where you think it might be. I look at something like rosuvastatin here and I say, well, halfway between 0 and around minus 70. Okay, well, that's going to be like minus 35, and it hits that probably close to around somewhere in the 5 to 10-ish range. So that might be a good initial estimate. So you construct them that way. So you could probably eyeball those. N's a little tougher, other than the fact that it doesn't look like it's grossly different from 1 in most of these. So anyway, you can imagine getting rough estimates for some of those just by eyeballing the data. Anyway, so we've got them. So this is going to generate our initial estimates. I've got this set up in such a way where there's certain parameters you're going to want to get from that you're going to want to get sampled during the MCMC simulation process. And some of them are going to be parameters where you really want to explore what their posterior distributions look like. Those are ones where you're going to want to look at things like history plots and density plots and so on. Those I specify here under the name parameters to plot. So this is just a vector of parameter names for those that I want to look at that way. Those are generally going to be sort of your main parameters within the model. That's going to be your fixed effects as well as your variance terms. But there's other random variables that you may also want to monitor and use for various diagnostics. And those are going to be things like your predicted values and maybe also individual random effect values. And that's what you see listed right here. So you can say I've captured the individual prediction, the population prediction. Here you've got this PCLDL mean pred. That's basically that's kind of like your population prediction without residual variability in it. And then finally your random effect here, the E0 term. So those are things that you would change as a function of the model. The next few lines those would normally stay the same. And then finally, the business end of this is right here for actually running WinBUGs. Things that you would change would typically be things like the number of chains, how many iterations you want to do, how many of those iterations do you want to use for burn-in. In other words, those would be the ones that you're going to discard to allow it to converge, and it's only those that are generated after that you would retain. And thin refers to thinning, and just to make sure you're clear on what's going on here, so we're going to run 3 chains of 10,000 iterations each. 4,000 of each chain is going to be thrown out as burn-in. So, and of those 6,000 per chain that are remaining, only every 5th one will be retained. So what does that mean? That means we're going to have what, 1,200 from each iteration, or 3,600 total samples will be returned for each one of our parameters. Now, let's see, I'm not going to step through all the components of this. Some of these you can ignore. If you're working in WinBUGS, this is set up so it'll work on either. This last four statements basically do nothing if you're working in Windows. They're useful if you're working in Unix or the Mac. But you can just leave them there. They won't hurt. They'll work on either platform as they are. The main things that you're likely to find yourself changing are these two right here. In fact, I think when I distributed these, they were actually set differently than what you see here. When I'm when I'm working on a model initially, before I've really gotten things down to a clean run, I will typically set clear WD to false. Clear WD means clear working directory. What it does is, if you set it to true, it will delete a lot of sort of intermediate files that are in there. It'll delete the individual initial estimate files, the data file, the script file, a log file, things like that. It will just delete them. And all you'll retain is basically what gets returned in the R processing here. During debugging, it's sometimes useful to have those files around. So usually when I'm doing my model development, I set this to false so it doesn't delete them. Debug equals true. As far as I know, it only does one thing. When debug is true, it means that when WinBUGS finishes, it will stay open. And in fact, it won't return control back to R until you actually physically go in and stop the WinBUGS run. You have to exit the WinBUGS run. Again, for when I'm working early on, I'll often set it to true so that if WinBUGS hits an error, I can actually still see the error message within WinBUGS. So again, during early model development, I'd recommend these settings: false for clear WD and true for debug. Once you have something running cleanly, you can go ahead and change them back. So this is actually going to do the WinBUGS run. All the MCMC samples are going to be stored in this object called BugsFit, which is a rather messy looking list of various things, but amongst the things that are in there, it will contain the MCMC samples. Save model is a function which saves a bunch of the results to basically it creates a new directory inside the example directory and stores the results inside of that. It's also where it'll ultimately be writing the various plots and things like that. So again, that's something you would normally not change. So ditto here. This is actually just taking some of the results in BugsFit and reformatting them to create a fairly simple matrix of your matrix of the MCMC samples that we'll be operating on subsequently to that. And then we've got a whole bunch of things happening down below. Maybe before we do those, why don't I go ahead and jump in and illustrate the first part of this running before I even talk about some of the rest of it. So why don't I go ahead and illustrate the process of running this. Now you can actually run the entire script in one go if you want. Typically I don't. Typically is, again, when I'm still working early on, before I know whether the bugs model is actually going to run correctly, I usually only run a subcomponent, subset of it to begin with. So let's go ahead and first thing I'll do even before I launch bugs is I'll just run everything up to but not including the bugs run just to make sure everything's working. Actually, you know what? I don't think I have an R session open. I need to do that first. Okay, let's fire that up. So we got an R session. Let's make that bigger too. Okay, let's actually separate that off in a separate window here. Okay, so let's go ahead and run everything up to this. Take a minute. Oh, I did a dummy. My setup is a little bit different than yours. I forgot when I commented this out that I needed it. Let me clean this up. Okay, let's do that again. By the way, feel free if you've got questions or anything, go ahead and ask anytime while we're plotting through this. Okay, let's fire that up. Okay, it seems to have done what it's supposed to do. Okay, why did that shrink back down again? Okay. Okay, so I don't see any error messages, so it looks like it went along on its merry way. So we've got various things in here. Is there anything we want to look at? Probably not. No, there's nothing too exciting to look at. So it ran okay, so let's go ahead and do the bugs run. So I'll just go ahead and grab that section right there and run it. You'll see it'll look slightly different in the Windows environment, but not humongously so. You can see it's launched a WinBUGS window. So that's going to take a little while here. Another good reason why if you have any questions, now's a good time to ask, because it'll take a few minutes for that to run. So that's going to go ahead. You can see it's actually going through the burn-in runs here. So recall that was 4,000 iterations, or you can see it's got the thin updater here, an update of 800. So 5 times 800 is 4,000. That's the 4,000 iterations that it's going to do for burn-in. Okay, so I did those. Now let's set a bunch of all the various things that we said we wanted to monitor. It's run set commands for those, and now it's doing the post burn-in sampling now. Yep, like watching paint dry. Okay, boom, it's done. Now, if you actually wanted to, you could look at the log file that's generated, or the log component here. I don't recommend spending a lot of time there, because it basically creates plots for everything under the sun here. But it is there if you wanted to. But it appears to have run successfully. We haven't had any hitches along the way, so we can go ahead and exit out of that. Again, remind you what debug, by saying debug equals true, it stopped here and stayed. If I had said debug equals false, the window would have closed on its own and would have gone back to R. So we close this. It usually takes a second before it finishes shoving everything. It still hasn't quite finished moving everything to R. There we go. Now it's back. So now we've got this big thing called bugs fit. I mean, if you actually looked at, let's see, we tried to look at kind of what's in bugs fit. If you've never done that, you can see there's a whole slew of things in here in the form of a in a fairly complicated list structure in here. So I won't go through that in detail. If you're curious, I recommend doing that along with looking at the Art of WinBUGS documentation. So it appears to have run. We can now work with that. Let's go ahead and one of the things just point out here. So since we said clear WD was false, you can see there's a whole bunch of other things here, a bunch of files. These are intermediate files that would normally be deleted. So you've got things like that log that we saw is there both in the form of a bug specific structure here as well as a text file. There's the script that was used to run WinBUGS. There's the initial estimates files here. There's the data file. And then these CODA files contain the MCMC simulations in there. So these things are all available. In particular, you have the script data and initial estimates files that allow you to sort of run bugs manually if you need to do some debugging. Okay, so they're there, but since it ran successfully, we no longer really need those. We could actually choose to delete them if you want. Anyway, the one thing I was going to point out is notice there's no subdirectories inside stat and gemcabine at the moment. But once I run save model and run that, you'll notice it generates a folder here called stat and gemcabine, and inside that it's moved a bunch of the files. It's moved some of those intermediate files, but in particular it's moved a copy of the R script, the model file, the statandgemcabine.txt, and it's also moved something here it calls statandgemcabine.fit.r save. That's actually a binary copy of the bugs fit object. The reason for doing that is if you want to do some of the subsequent analyses of the bugs results without actually rerunning bugs again, you can do that. For this run, the run time was, not 0, but it wasn't terribly long. But if you're doing a long run that takes hours or days, it's nice to be able to just have that there and be able to reconstitute it without rerunning the whole thing. I also have I'll just mention here, there's a line here that's commented out where it's this load. If you actually do ever need to you just want to reconstitute the bugs fit object without rerunning bugs, if you uncomment that line and run it, that will actually read that. It will read the bugs fit object from this rsave file that's in here. So sometimes that comes in handy. Okay, let's go ahead and restructure this. And then the rest of this is going to be various plots, building some plots and tables. Let's go ahead and fire some of this up. Let's see, this part here, this one block right here, that is almost all bugs runs that I ever do is almost always the same. So it's unlikely you'll be modifying this section. The things that come after that will be various kinds of plots that may be different. In fact, typically will have to be different depending upon the specific kind of problem. But this part of it usually remains the same. So let's go ahead and launch it. I'll just mention what's here. Here, this is doing nothing more than opening up setting the thing up to create PDF files for containing the graphical results. Let's see, this is taking taking the MCMC samples and just pulling out the subset that we actually want to make plots, so that, recall, we had that thing called parameters to plot. Well, this is just pulling out those and putting them into an object, and then that's going to be operated on by this statement, which uses this function, which is inside the bugs tools stuff, which generates a nice table summarizing the results. In addition, it creates some history plots, which we'll look at in a minute, and density plots as part of that, as well as some here is the Gelman-Rubin-Brooks plots, which are used for convergence diagnostics. And then the last statement just grabs the table that generates and writes it to a file. Let's just go ahead and run it. Boop. Okay. Finished with that part. Let me show you something of what that has done for us. It's created this file here, the statingemcabine.summary.csv. If we open that up and make it a little bigger, hopefully that's not too tiny on line there. This is a summary table for the parameters that we put in our parameters to plot thing there. The first item here, deviance, will usually appear in these by default. That is roughly equivalent to the now I always have to go and remind myself which it is. So this is what, -2 times the log of the likelihood. This is summarizing that. Then we've got our various parameters in here, and for each one of those we get our sort of an estimate of the posterior mean. Now what this is actually it's a mean of the MCMC samples. Now the MCMC samples in an ideal world would be good representations of the posterior distribution. So this is intended to be an estimate of our posterior mean. This is a posterior standard deviation. We have a couple things here, one called a naive standard error, which is nothing more than taking the standard deviation from the previous column and dividing it by the square root of the number of MCMC samples that were used to calculate it. But keep in mind that MCMC samples are correlated. They're not independent samples, and as a result, the actual standard error is actually typically going to be greater than or equal to the naive standard error, and this, what they call the time series standard error, is an attempt to adjust for the autocorrelation to get a more appropriate estimate of the standard error. And this is, by the way, a standard error in the posterior mean. Then we have some posterior quantiles here, the 2.5 percentile, the 25th percentile, 50th, 75th, and 97.5. So you get an estimate of your 95% credible interval by looking at the 2.5% and 97.5% value. And then finally, a number I find useful as sort of a diagnostic for whether I've got an adequate number of samples or not, is something termed the effective N, which is an attempt to estimate the equivalent number of independent samples that these samples represent. Now, if these were really independent samples, I would expect for our run for these numbers to be like 3,600, because that's how many MCMC samples we retained. But as you can see, they're smaller than that, and many of them are a lot smaller than that, which is sort of a warning sign. So some of them don't look bad. The deviance, the zero mean, you can see are north of 1,000. But then I've got things like Emax statin of less than 20, N statin less, it's still only around 30. I got another one here, what's one of the ED50s around 17. And in fact, you can see all of the ED50s here for the statins are all south of 20 in here. So those are indicating problems. That means I almost certainly don't have enough samples, and since I ran a fair number of samples, that suggests we've got a pretty severe autocorrelation problem, possibly a convergence problem, though I can't tell that from this number. So that's one of the reasons for looking at something like effective N. The other thing that gives you a similar kind of information is to look at the time series standard error as compared to the parameter estimate. Okay, so that's one of the things it generates for you. The other thing that it generates is some plots. Let's go ahead and look at a couple of those. First things it gives you is some history plots. And the warning signs we saw with those low effective N numbers are becoming quite apparent now when we look at some of these traces. You can see like the deviance and the E0 mean don't look too awful. You know, they're more or less fuzzy caterpillars. You know, I'd probably want a few more samples, but it's not too bad. There's no clear convergence issue, just maybe more samples might be nice. But up here, things are looking pretty ugly with the ED50s. At the very least, we have an extreme autocorrelation problem here, and going by how much they've diverged, there's probably a convergence problem too. Again, Emax statin doesn't look too great either. It's also pretty highly, one of the things, if you look, it's too bad they're not on the same page. Oh, we can look at some of the lower ones. Notice that some of the patterns in the Emax statin are reflected by the ED50 statins. So there's an awful lot of correlation between those, a not uncommon problem with Emax type models. So one of the first things you'd look at is say, well, I'm not going to use this for making inferences based upon what I see here. It doesn't say that the model is bad, but it does say that our model estimates have a problem in here. But anyway, that's one of the first things we look at. So at this point, my reaction is either I'm going to have to do a whole lot more samples, or I need to find some other strategy to try and improve the MCMC estimation behavior. But let's go ahead and plow through the rest of this. You can see here we've got our univariate density estimates here. For all of these, I guess our marginal density estimates for the various parameters. And then it also shows the Gelman-Rubin-Brooks plots. Basically, what you're looking for here is you're looking for things like, let's say we can start by looking at, say, the black curve on these. You're looking for these to converge towards 1. And certainly to be less than around 1.05. And you can see that's certainly not true for many of these, particularly these the ED50 statins are looking pretty bad here. Okay, so that's as far as we've gotten with that. Let's go ahead and run the rest, though we've already seen here that we've got a problem we need to rectify with the model. But let's go ahead and I'll go ahead and illustrate the rest of what's going to happen with this script. Some of the next things I do here is do some posterior predictive distributions in here. Let me go ahead and run those. I won't go through detail how they're structured. It'll probably be best to see what they look like rather than have me explain it. I'm just going to go ahead and plow through these. In fact, let me just go ahead and write to the end on this. Go ahead and run it. Actually, if it's scooting along, we might be able to show you some of these as it's going. Okay, so that one of the functions here, this is one approach to looking at posterior predictions. And you can think of this as a posterior predictive check. What did it just do? Here we go. Let me go back to the beginning. Now, in this case, I'm not going to believe these too much because we know we didn't converge well, but I at least give you a sense of what sort of information it's going to generate. So what you're looking at is the black dots are the LDL percent mean changes. Actually, it's the mean LDL percent change from baseline, and the black dots are the observed data from the various plots. In this case, we're looking at atorvastatin monotherapy in here as compared to placebo. And the red vertical lines here represent the posterior medians, or really the medians of the MCMC samples, and then the blue curves represent I believe they were 95% credible intervals for those predictions in here. So we're looking for reasonable consistency here. These have been oriented so that they've been ordered such that within each dose group, they go from the lowest to highest. So there's nothing coincidental about the fact they're going up. It's just the way they were sorted in here. So you can see it's pretty well describing these. And we go through this for the various statins. There's lovastatin. By the way, the placebo group in this is identical for all of them, so you don't really need to, once you look at it for one, you don't really need to look at it for the rest. Pravastatin, rosuvastatin, simvastatin, and then we go into the non-statin monotherapy. We've got ezetimibe, gemcitabine, and then some of the combinations. Here's combinations with ezetimibe. In each case, they're also compared with the corresponding monotherapy, so you can get some sense of that. And goes through that through the various statins combined with it, and then finally the atorvastatin gemcitabine combinations in here. Those were the individual predictions. So and now we're looking at the population predictions. So as expected then for the population predictions, the posterior median should be essentially identical for a given dose in here because we didn't have any other covariates in there. So those should be pretty much identical. And that's what you see here. The confidence bands are different because the sample sizes are different. And so we go through that whole mess all over again for the population predictions. And then I've got a few other diagnostics I won't spend time on now, but because there's other things I want to hit on here. So it just goes through things like looking at the distributions of the various, well, in this case, there's only one random effect, E0, so it goes through the posterior distributions. In this case, the distribution of the posterior medians of that. So it steps through that, does the same thing for the residuals. So it has various kinds of residual plots in here. I think that's it. Yeah. So that's all the results on that. Now let's step back, and again, we have a problem here that we know we don't have an adequate estimation from this given the behavior of the MCMC samples. We have some extreme autocorrelation, and one hypothesis would be that extreme autocorrelation may be secondary to the extreme correlation across the parameters, particularly things like between Emax and ED50, which appear to be pretty strongly correlated with each other. And we could do some plots to look at that. If you do sort of pairwise plots of those parameters against each other, that some of that might give you a clue on that too. But it was pretty evident just looking at the patterns in the history plots. So how might we do something about that? And one approach that can sometimes work is to try and reparameterize a model so that the parameters you are sampling are less correlated with each other. And that's one strategy I was going to show you here. Let me pull up the slides again. That's not what I wanted. There it is. Okay, There we go. One trick that I found often helps when I'm working with Emacs models is a reparameterization, and I've seen a couple other reparameterizations that are similar sort of idea, and likely would probably work also work reasonably well. But the parameterization I'm going to use is one that that I described a number of years ago and sort of labeled as a truncated Emacs reparameterization. But the basic idea is, instead of using the Emacs in its original form, you reparameterize it in terms of, instead of having Emacs as the primary sampled parameter, I'm going to use something which we labeled here as E star. And this E star would be essentially the effect at some arbitrarily specified concentration, or in our case dose, which is here labeled as C star. And you would typically pick that C star to be somewhere within the range of observed values. So in our case, where we're going to be working with an ED50 here, we would pick a dose that's in the range we're actually working with. And then the E star would be a predicted effect at that. And then the ED50 and the Emax then get calculated indirectly from those. But the idea is that if you actually work with that observed value, that, or something that's within the range of observed values, it's likely to be a lot less correlated than this thing which is being extrapolated out, the Emax, which ends up being highly correlated with the ED50. So that was not a very coherent explanation, but why don't we illustrate it by actually doing it? So we're going to apply that to our example here. It ends up slightly more complicated because we have different ED50s for all of the statins. So what we'll do is basically use that truncated Emax reparameterization for one of them, and we'll pick atorvastatin as our reference in this case, and then the rest of them get derived from that one. So that's the idea here. So here's that reparameterization shown, where the parameter we're going to estimate, instead of directly estimating Emax and ED50 for atorvastatin, we're going to estimate something called E star statin here and something called B for atorvastatin, which are related to Emax and ED50. And you can see it in here. N-statin we're just going to leave as is and try to estimate it on its own, though it too is actually correlated with those other two parameters. So we're going to do this. And in particular, we're going to pick, and of course this E star statin then would be the predicted response for a dose equal to D star statin. Again, this is going to be specifically for atorvastatin. So what we're going to pick here is, I arbitrarily picked it. It's actually the highest dose that was used in most of these trials, which was 80 milligrams per day. So we're going to pick that. So that one's a fixed quantity, but then E star is an estimated quantity. So that's now going to be our predicted effect for an 80 milligram dose of atorvastatin. And then B, our B statin here then we've got one for atorvastatin, which is going to be an estimated quantity in there. So for atorvastatin, you can see then you get your Emax according to the equation here on the right, in terms of both that B and the E star parameter. And ED50 actually comes from just the ratio of D star over B statin. And then we're going to specify the B value. Now, the B value is going to be different for each of the other statins here, and that's going to be done by multiplying the one for atorvastatin by some other scaling parameter. So basically this pi statin will be 1 for atorvastatin, but it'll be some estimated quantity for all the remaining ones. So we're going to basically just, all you have to do, and it turns out, is just redo the priors in order to make this work. So this is basically how we're doing it, is according to this relationship. The priors are now specified in terms of our new parameters, E star and B, and the various pi statin terms here. And we're going to run that. See, I don't think I have anything in the next slide. Excuse me. Oh, okay, that's right. I also did the same thing for ezetimibe and gemcitabine. So same story here. I'm going to use the truncated Emacs parameterizations for all of them. So let's go ahead and see what's involved in that. And let's see, was this one? I think, let me just double check something. I'm trying to remember if this is one I distributed to you originally or not here. Let me just pull up the course website here because I wanted to point out something there anyway. Oops. And okay, yeah, I believe the original one I did distribute to you. Okay, so I just wanted to point out that there's some additional examples that we may or may not have time. It looks like we may not have time to actually get into them today, but you may want to go ahead and download them that I posted on the website here. Okay, so in your set there should be something called statin gemcitabine. Where'd it go? There it is. Statin gemcitabine trunk Emacs in here. And the only part that's really substantially different is when let me go ahead and open up the model. Yeah, that's not what I wanted. There we go. First part of the model is the same. Where things get different is down here in the prior distribution. So now you can see the priors are being specified in terms of these things, like we've got, the B's and the E star statin, B statin, pi statin in here, and then it goes through a similar litany in the non-statins. And then as a separate step, it then calculates the Emaxs and ED50s from those. And as a result, the top part of the code all looks the same. It's only in the priors where these things change. The critical thing is that the Gibbs sampler will now be working with a different set of parameters when it constructs the marginal distributions, and it'll be working with parameters that we hope are less correlated. Okay, so that's the main difference. If you pull up the script, again, the main difference there is going to be that the initial estimates are going to be oops, wrong one. Where do we go here? There we go. The initial estimates are going to be in terms of these new parameters. So again, we've got E star and pi and B in here. So that had to be changed in order to do this. And you didn't really have to, but I did go ahead and collect some of those new parameters too, in addition to the ones we were already collecting. Now, let's go ahead and just, where are we at here? Yeah. Rather than run this right now, because that's going to take a few minutes, of which we have a limited amount left, let me go ahead and do the Julia Child thing here. And let's just go to, go to the solutions directory. and pull out, there we go, statin gemcitabine trunk Emax. Now, if we look at this one, let's go ahead and pull up the our summary table here. Okay, the main thing I wanted to highlight here is this last one. Now recall that things like the ED50s, we had effective ends that were on the order of less than 20. Take a look at them now. Let me highlight. There's our ED50s. They're now in the hundreds. Maybe not optimal. I'd probably like those maybe more into the thousands, but I'll take something north of 200 better, over something south of 20 any day. If any of my inferences were really highly dependent upon ED50, I'd probably run more samples. So I'd probably run anywhere from 5 to 10 times more samples to maybe bring these numbers above 1,000 in order to do any inferences, particularly if I want to say anything about the tail probabilities. But that's substantially improved. And if we take a look at the history plots, you'll see again something quite different. Recall that these look pretty well. Those are the B statins. Let me go find the get the ones are ED50s. So it's a little harder to tell than these, but these are definitely markedly improved over what we had before in here. Let me go on. Again, the Emaxes are definitely a lot better. ED50s are better. Again, I'd probably still run maybe on the order of 10 times more samples to be clear, but to be happier with this. But these are markedly better than what we saw before just by making a reparameterization on this. So so we now would have something where even 10 times more, though that's certainly a measurable amount of time. It's not outrageously onerous for an analysis like this. So that was the main thing I wanted to bring out with the truncated Emax component. Actually, let me take a look at my notes, see if there's any other goodies I wanted to make sure I hit on before we vanish today. Oh yeah, I wanted to summarize. I wanted to give you an exercise. Why don't I do that before I do anything else? So if you have any questions, go ahead and post them here. But what I wanted to do is give you guys an exercise that we'll go over on Monday. It's actually kind of a subset of what I just walked through in order for you guys to sort of get your hands dirty with this without necessarily having quite as many complications as the example I went through. Okay, so our hands-on problem, I probably need to renumber these now that I'm not sure that hands-on problem 3 is still correct anymore. But anyway, we're going to look at a dose response model based on sample means, just like the example we did. And again, we're actually going to be looking at LDL percent change from baseline, but looking at a subset of the data. We're just going to look at atorvastatin and rosuvastatin. So we're going to explore the effects of those two statins on LDL percent change from baseline. The data here are all extracted from public sources, and I guess you can imagine a possible objective of the analysis would be to compare the dose response of these two compounds. If you could imagine that if you were, excuse me, in developing, if one of these was a new compound you were developing, this might be the basis for maybe selecting a dose for your compound. Actually, let me enlarge this. Okay. The data here are going to be sample means for our LDL percent change from baseline at endpoint, coming from 12 studies corresponding to 56 treatment arms. They correspond to a 6 to 16 week treatment duration. We've got some covariates that could be used in the model, baseline LDL and treatment duration. The exercise here will be to construct a model for LDL percent change from baseline as a function of drug and daily dose and possibly some other covariates. And I recommend that you go ahead and try both the standard and truncated Emax parameterizations to get a handle on that. The example is inside of a direct, whoops, I shouldn't put the strike through there we go. It's inside of a directory called statin hands-on, which should be in your course materials. And the data set itself is in there. It's called ldldata.csv. This is just showing you some exploratory plots of the data that you'll be working with. I give you a proposed model. This is essentially just a subcomponent of the model that we were looking at for the combination treatments. And it's really, if you look at that, you'll see it's basically chopping off pieces from the other one. So, and some recommended priors to try, and something you may want to entertain is exploring other options for priors. Okay. So that's going to be your job between now and Monday, is to take a look at that and attempt to implement that. My recommendation is, to approach this, if you really want to sort of learn how, is let me actually point you to the directory here. Now, the directory actually contains what you could think of as sort of a solution to the problem. Where'd it go? Statin hands-on. Here it is. Oh, I'm in solutions. I don't want to be in solutions. Here we go. So what you'll have in there, I think, is the same as what you see. Okay, let's just stay with the original one. Is what you see right here. The data that you'll work with is this one, the ldldata.csv. Now it actually has an R script and a model in there already. My recommendation, if you really wanted to get a better handle on this, and it depends on how comfortable you feel working with R and WinBUGS, would either be to well, actually, my real suggestion, if you really want to learn it, would be to attempt to build the bugs model from scratch, but use the statin gemcitabine example. Where to go here? Use the statin gemcitabine example for the R script as a template, and modify it as necessary for however you construct your model. If that seems a little too daunting to build the bugs model from scratch, then the other alternative would be to take the statin gemcitabine model itself and modify it. Go ahead and try and edit that to be appropriate for the case, and you also use that as a template for the example. So anyway, that's just kind of my suggestion on how you might attack it in order to learn it more than you would just by sort of grabbing the script and model as they've already been generated here. Maybe move these, maybe copy these somewhere, and recreate them anew. Another thing that maybe if we have time on Monday, maybe I'll take a look at is we can also do the examples I just showed you, where we use the observed standard errors rather than that model estimated variance component. That's actually available to you as, where'd it go here? It was called statin gemcitabine 2. That's one of the additional examples that I posted to the course website. So if you wanted to see how to do that, that it might be worth a look at that. Anyway, feel free to take a look at it, and if we have time, maybe we can take a look at that on Monday also. So let me stop here, see if there's any last questions before I disappear. Okay, I don't see anything popping up on the board, so I guess I will just say goodbye till this coming Monday then. See you then.